Hello. Excellent. A few people, here. Amazing. So we're going to talk about momentum again. I know last week we spoken about momentum, and I feel that it's going to be more useful than talking about triangles. So I have 6 questions prepared, 4 reasonably easy ones, and 2 tough ones. Okay, so let's go for it. Most of my problems are in 2D-ish. So momentum and impulse part 2. Welcome everyone. Let's start. So a cannon of mass 1,000 kilograms shoot a 20 kilogram projectile at 200 meters per second at an angle of 30 degrees. What is the recoil velocity? Okay, so there's a cannon. Okay, some sort of cannon, and it shoots a projectile, and at 200 meters per second, and the angle is 30 degrees. 30 degrees. The cannon is 1,000 kilograms, and this is 20 kilograms. So as a result, the cannon will recoil. Well, it can't recoil in the opposite direction to the projectile, so certainly it will recoil backwards with a velocity, let's call it u. Okay. Now, we know that momentum is conserved in any direction, given there are no forces in that direction. So no horizontal external forces, no horizontal external forces. That means momentum is conserved horizontally. Okay, so all the momentum in the horizontal direction will be conserved. Does that make sense? Do you understand what I'm talking about? All right, so that means what we can do is we break down the velocity into horizontal and vertical. And the horizontal velocity is 200 cos 30, and this is 200 sine 30. Okay. So before the total momentum is 0, of course, because they're stationary, both stationary. And after, so 200, so right, let's call it M, let's call this big M, M. So M multiplied by the velocity, multiplied by cos 30, plus the momentum of the cannon, its mass times u, and that has to equal to the initial, which so must equal to 0. And therefore, because we know the mass, we know the velocity, we know this, so we can calculate u is equal to minus mv cos 30 divided by capital M. So that's minus 20 times 200 times square root of 3 over 2, cos 30 square root of 3 over 2, divided by 1,000. And that is 10, 1,000. So 2 minus 2 root 3. which is approximately 3.4 meters, minus 3.4 meters per second. The negative means 3.46 technically, 3.46 meters per second. Right, so that's the recoil velocity, 3.46 meters per second. Okay. Now, is momentum conserved in this direction, in this interaction? Why would I ask that? I mean, I just use conservation of momentum. Can somebody clarify? Is momentum conserved? Or we can let's ignore the exhaust gases. But all right, is momentum conserved? So let's work it out. Momentum conserved, question mark. Well, let's figure it out. So initially, they're both stationary. So the total momentum, as I already mentioned, is 0 because initially they're stationary. However, at the after, so let's do the horizontal momentum. Horizontal. So that's going to be 200 times cos 30 times the mass, which is 20, plus 1000 multiplied by minus 3.46. And you will, if you do that calculation, that would be 0. So horizontal is conserved, yes. Conserved horizontally. Horizontal. Now, vertical. The cannon is not moving vertically, so that's 0. But this is 20 sine 20 multiplied by 20 multiplied by 200 multiplied by sine 30, which is 4,000, that is 2,000 kilogram meters per second. So not conserved. Conserved vertically. So the vertical momentum has increased, but the horizontal momentum has not changed. So what's going on? Why is horizontal momentum conserved and vertical momentum not conserved? There's a hint. Ooh, Luke, yeah, it would. Well, it depends on how you look at it. No horizontal external forces. That's why momentum is not conserved. But there is a vertical external force. Vertical external force. Vertical external force. What is the vertical external force? Luke mentioned it. It's the normal reaction. Normal reaction, which is therefore momentum is not conserved vertically. Okay. There is a normal reaction here. the normal reaction force on the cannon, that means the vertical momentum is not conserved. Does that make sense? Do you understand on a scale of 0 to 10, please? Exactly, Parachita. Momentum is only conserved if you have no external forces. And that's what the conservation of momentum says. With no external forces, momentum is conserved. But I mean, it's a very obvious thing if you think about it. Take this pen. It's stationary. And when I release, its velocity changes. Therefore, the momentum changes. Why does it change? Because there is external force. What is the external force in this case? What is the external force that causes the pen to change its velocity? The weight. Yeah, well done. So the weight causes it to accelerate. Now, if there are no external forces, it would remain stationary. Question. It's not related to this, but question 8 in the assignment. Do we have to draw a diagram showing the direction of pieces that have gone in? Are you talking about, is that the firework question? Well, yes. You don't have to. You can write it in words, but I think it's easier if you draw it. Why not? Okay. Now, the second question is very similar to the previous one. A projectile of mass 50 kilograms traveling with velocity 800 meters a second at 30 degrees to the horizontal hits a railroad car. Find and get stuck, of course, because it's sand. So you have a railroad car with sand. And there's a projectile that hits the sand at 800 meters per second. That's more than double speed of sound, but whatever. 50 kilograms. I think the sand would go everywhere, but that's fine. So then this is 16 tons, so 16,000 kilograms. Of course, it's on tracks. And once it gets stuck, the whole system with the projectile stuck will be traveling at velocity u. Okay. So this is before, and this is after. It's a stationary car. Who's firing a cannon at sand? Obviously physicists. Who else? Who else would do that? Okay, so we have 30 degrees. 30 degrees. So the total momentum. We can only consider horizontal momentum. Horizontally. And this is going to be 800 cos 30. So 50 kilograms. I kind of want to do it in letters first, but never mind. 50 multiplied by 800 cos 30 plus 0, because this has 0 momentum, equals, now 50 plus 16,000, that's the mass of the system, multiplied by u. And that's it. That's literally it. That's the end of physics. Now where you just need to find u, which is 50 multiplied by 800 cos 30 and divided by 16,050. 16,050 is literally the fourth significant figure, so it wouldn't really play a role. So you can actually ignore the mass of the projectile itself. 50 times 800 times cos 30 divided by 16,050. 2.16. 16. What's the horizontal? If I saw this in the equation, I'd assume the horizontal was the ground. Well, yeah, horizontally. That's in the horizontal direction. To the if you assume the ground is horizontal, because the ground can go up, but the horizontal is still like that. The solution would not matter. If you had a projectile from the bottom, being fired from the bottom, it would still be the horizontal momentum is still velocity is still 800 times cos 30, so it wouldn't make any difference which direction it is traveling. But I mean, it would be really weird if somebody was firing a projectile from the bottom. More likely from the top. Okay, the next question is slightly off topic. It's a section that we decided to pretty much remove from the assignment, but you will have fun with it in year 12. A person of 60 kilogram walks from one end of the boat and of a length 3 meters to the other. How far will the boat move? What on earth are we talking about? So this is a man in a boat. What happens if the man walks to the other end of the boat? What's your prediction? Right? The boat moves backwards. Could be. Could be. Move was in. Okay. If you think about the man, the center of the man is approximately where this orange peel is. I assume that's an orange peel. Do you think the person would end up further down, or the person will stay where he is? Or would the person move backwards? So the person would stay where he is, but the boat would move backwards. Okay, let's see. And perhaps Parachita was right. I think he ended up slightly further down as the friction with the water non-zero. That's a good point. But what if there was no friction? What would happen then? Okay, let's watch. Okay, so what happened? Yeah, he's not where he is. He has moved slightly. He has moved about the length of this distance, right? So the center of the man is somewhere here. The man has moved, and the boat has moved to the other side, which is quite cool. So two things are happening. The boat is moving backwards, but the man is moving forwards, but not as fast as you would think. Okay, so that's one thing. I'll show you the other experiment further down. A person walks from one end of the boat. So what we have to consider here is called the center of mass. The center of mass of a system. So we have a boat. And it's 120 kilograms. The center of the mass of the boat is usually in the middle. So that's the center of mass of the boat. Center of mass, boat. The person is standing here at one end of the boat. So that's the center of mass of the person. Now, the boat is 120 kilograms. 20 kilograms. And the person is 60 kilograms. So where do you think the center of mass of boat plus person would be? One third of the way to the person one third of the way from the center of the boat, you mean? Yes. So if you have, so like this, and you would be correct. So if the whole length of the boat is 3 meters, 3 meters, this means that this is 0.5 meters. And this is 1 meter. So that's the center of mass of the boat plus person. Center of mass. Okay. So you could assume that the boat is a point, and it's right here. It's where the center of mass is, and the person is here, and this is the center of mass. Now, one fundamental consequence of the conservation of momentum, I won't prove it. I don't have time to prove it, but assume I am correct, and assume you believe me. Assuming you believe me, the center of mass can only be moved by external forces. That's one of the consequences of conservation of momentum. Consequence of conservation of momentum. And because there are no external forces, because the boat plus person don't have any external force except water resistance, which we will assume negligible. The center of mass will not move. Because there are no external forces, the center of mass will stay where it is. So by the time the person shifts to the other side, the center of mass will remain where it is. And that means the boat will be 0.5 meters this way, and the person would end up 1 meter the opposite direction. So this would be 0.5 meters, and this is 1 meter. and the boat would be here. So this is the center of mass of the boat, and this is the center. So the person would be here. So by the time the person walks to the other end, the boat would have shifted by how much? What's the total shift in the position of the boat? One meter, yes. The boat moves by 1 meter. Why is it exactly a third though? A third because it's 60 kilograms and 120 kilograms. And if you think about it, what would it take to balance two people on a seesaw? One is 120 kilograms and one is 60 kilograms. It's the other way around. Where would you put the pivot? And it turns out you would put the pivot exactly 1/3 of the way, because if this distance, if the whole length is L, this would be L over 3, and this would be 2L over 3. Does that make sense? So if you want the seesaw to be balanced, the center of mass has to be here. Well, technically here, but let's not go there. Center of mass has to be above the pivot. And yeah, so that's the what I want with this exercise. I want you to get an intuitive understanding what a center of mass is, and the fact that the center of mass doesn't move if you don't have external forces, like with the boat. So here, so here, okay. So here we have the center of mass of the man. The center of mass of the man is here. Center of mass of the boat is somewhere here. The center of mass of the boat is, well, somewhere here. And if you take the center of mass of person plus boat, well, assuming the person is heavier than the boat, somewhere here and somewhere here. Okay, so the center of mass of system does not move. Not move. Okay. I think this but if a center of mass acts like a pivot on the boat, making the bad balance, surely the boat will never. Yeah, exactly. So the edge of the boat would be the pivot. So if the center of mass is inside, then yes. But if the pivot, let's say here, but I mean, way before that, you would get water. You would get water in the boat. That would cause the more mass on this side. And the center of mass would go over the tip and tip over. But yeah. So with that in mind, let's go to problem 4, which sounds. Oh no, sorry. That's there's another experiment. So here, the person is throwing a heavy ball. And what would happen when the person throws a heavy ball? Yeah, the boat moves backwards. So let's have a look. Now, let's have a look what happens if the boat lands in the canoe. You see how when the ball lands, if the previous one, the ball landed in the water. Here, the ball lands in the canoe. And the moment the ball lands in the canoe stops. But if the ball lands in the water, the canoe carries on going. All right. You can think about it. Well, you can only start moving if there's an external force. So what is the external force? Okay, let me. That's a really cool one actually, and a really non-obvious one. Okay, so he's throwing the ball, and the ball lands in the canoe, and the canoe stops. So there are no external forces. So the center of mass does not move, which makes perfect sense, right? No external forces, the center of mass stays where it is. Yes, the ball shifts to the left, the canoe shifts to the right, but the center of mass will stay where it is. Now, in the second scenario, and now the center of mass goes away. The center of mass shifts, obviously, because the canoe moves, and it will keep going. If there's no friction, the canoe will keep going. So what on earth is going on? How come the center of mass is changing position in the second scenario. Would the second movement of the boat change if the ball landed closer to the person in the boat? Would the second movement of the boat if it lands closer in the boat, it's just this would be a less of a shift because the ball would be in the air for a shorter time. So the ball in the boat. Yes, Ikshita. Yeah, I'm answering your question. So, all right. So let's talk about this. Throwing a ball in the boat. So there's a person and he's throwing a ball and the ball lands in the canoe. So ball lands in a boat. There's a push. So the person is pushing against the ball and that causes the person to move backwards. Person pushes the ball. The person and boat move right. Now, when the ball hits the canoe, ball hits canoe, causes it to stop. Center of mass does not move. So the ball moves to the right, the canoe moves to the left, but the center of mass stays where it is. No, it's exactly how it was in the previous one. Center of mass of the boat, center of mass of the person. Now, in this case, you have center of mass of the ball and the person. So the boat moves slightly to the right. Yeah. So let's delete that. So you have the center of mass. Let's say the center of mass is somewhere here, and here the center of mass is somewhere here. The person and boat has moved slightly to the right. The ball has moved to the left, but the center of mass did not change position. Does that make sense? Do you understand what I'm talking about? Okay, there's still 7 of you, so hopefully, yeah. All right. Now the ball lands outside the canoe. Ball lands in water. So you have the person and the ball, and the center of mass is somewhere here. Well, see, he throws the ball lands somewhere here, but the canoe keeps going. The canoe keeps going indefinitely until water resistance stops it. And the center of mass will probably be somewhere here. Nothing to stop the canoe. Nothing to stop canoe. Canoe travels indefinitely. So what's going on? We're not just contradicting what this says. Center of mass can only be moved by external forces. So what is the external force in this example? Mark, center of mass of the boat moves, yes. But the ball also moves. So the ball moves left, boat moves right, the ball moves left, boat moves right, but this overall center of mass stays where it is. But in the second case, it doesn't. The ball travels, it lands in the water, but the boat keeps going, and after, I don't know, 7 minutes, the boat will be on the other side of the lake if there was no water resistance. Being pulled slightly less, the buoyancy. That's an interesting example. It's actually something unusual. The external force is quite bizarre. It is the water resistance on the ball that is in the water. When the ball hits the water resistance causes it to stop. That means there's a water resistance on this ball. Water resistance. And that is the external force that causes the center of the mass of the system to move. It probably sounds crazy, right? Because how can water resistance on the ball cause the boat to move? This makes no sense whatsoever. But that's how it is. You push against the ball. You push against the ball. It causes you to move back. If there was no water resistance, the ball would keep moving indefinitely. And that makes perfect sense. If you throw a ball, the ball moves one way, you move the other way. That makes perfect sense. But the ball hits the water, so there's an overall change in momentum because of that water resistance force that causes the boat to stop. If you were on a frictionless surface, you would throw the ball and you would move forever, and the ball would move forever. But because there's something to stop the ball, well, the ball stops. And the position of the center of mass changes not because the water resistance is pushing you somehow. It's because the water resistance is preventing the ball from moving indefinitely into the yeah. So the center of mass is changed. Center of mass is moved by an external force, which is the water resistance on the ball, which sounds bizarre, but I mean that's how it is. Because it's just to clarify, when you throw the ball, regardless where the ball is in the air, would the center of mass shift away from the person? Yes. The center of mass would move away from the person till the ball lands back in the boat and the center of mass of the boat shifts back. No, it would not shift back. Look, maybe I haven't drawn it properly, but look. Here, before you throw the ball, if you're throwing the ball into the boat, you are closer to the center of mass of the system. This is the center of mass of person plus ball plus boat. Center of mass of three objects. You are here, you are this distance away from the center of mass. But you end up further away because the ball has moved. The ball has moved to the other side, so the center of mass is now between you and the ball, slightly closer to the ball than, well, no, slightly further away from you. All right, so this is talking about center of mass. How how well did you understand the ideas that I was trying to okay, how well do you understand this statement? Center of mass can only move by external force. On a scale of 0 to 10, please. Okay. All right. So, okay. How well do you understand that the center of mass of the man plus boat does not move in this diagram, in this example? On a scale of 0 to 10 again, please. How well do you understand that the center of mass does not move? Because it doesn't move because there are no external forces. There's no horizontal external forces. Nothing is pushing the boat horizontally one way or another. Only internal forces. That means the man is pushing the boat and the boat is pushing the man. Basically, in this diagram, so let's say, for simplicity, let's say the man is 60 kilograms. Let's say the man is 60 kilograms and the boat is, I don't know, 40 kilograms. So this is the boat. This is where the center of the boat, and this is the center of the man. And this is the center of the boat plus man. Okay. Again, the man is 60, the boat is 40, the boat is here, the man is here, and the center of the boat plus man is here. So the person has shifted to the right, the boat has moved to the left, but the center of mass stayed where it is. Does that clear things up? The center of mass. Okay. Understand the man and boat, but not the man, boat, and ball one. Man, boat, and ball. In here, the center of mass does not move because there are no external forces. The center of mass does not shift. So the man, ball, and boat are in this position. When they land, the center of mass shifts. The center of mass stays where it is. Sorry. So the man and boat move to the right, the ball moves to the left, but the center of mass stays where it is. But when the ball lands in the water, when the ball hits the water, there's a resistance from the water. The water slows down the ball, causes it to stop. And that water resistance force is an external force because it's an external force pushing to the right. It's slowing the ball down. And that external force causes the center of mass of the system to move to the right. Not by actually moving the boat, but preventing the ball moving left. That's how it does that. Because there are two ways you can move the center of mass. You can, if you stop something, that causes a movement in center of mass. Okay. So I hope that clears things up. So don't worry, this is a complex topic, and I didn't even define the center of mass. It didn't even give you the formula how to calculate the center of mass. I'm just doing everything intuitively. Don't worry if you don't understand it fully. It's a really complicated topic, and we're not doing any questions on that. Okay. Problem 4. A projectile launched at 40 meters per second. At 30 degrees, at the top of the trajectory, explodes and breaks into 2 equal parts, which initially travel horizontally in the same plane. The first piece lands 30 meters from the launch point. Where does the second piece land? Okay. It sounds like a difficult problem. So there's projectile motion. There is 30 degrees. At the top, something happens. So we are shooting a projectile. It flies up. At the top, it breaks down into 2 pieces. And one piece goes that way, one piece goes the other way. And one of them lands somewhere here. The other one lands somewhere here. We know that this distance is 30 meters. So we need to find this distance. Sounds like a really difficult one. Until we remember what we were talking about a few minutes ago. The center of mass can be only moved by external forces. And there are no external forces. There's no horizontal external forces. No horizontal external forces. But here, the center of mass is already moving. Center of mass of the projectile will move as if nothing happened. All right, I'll try to demonstrate. So, bit projectile motion. Let's see 40. Sorry, let's make it 30 meters per second. 30 degrees. Okay, so here's a diagram. So if the projectile did not break, the center of mass would travel along the blue line. But at the top position, the projectile breaks down into, let's say, 2 pieces. And let's say one travels like this, and the other one travels like this. But at any moment in time, the center of mass of the two pieces, center of mass of the 2 pieces will follow the blue trajectory. So let's say there's a piece that's traveling like this. That means the other piece will have to travel like this. And the center of mass, if this is here and this is here, the center of mass will be here. And when it's here and here, the center of mass would be here. Here and here. So basically, by the time it lands, this piece will be here, and this piece will land here. And if they have equal masses, so the center of mass will land here. So no matter how the projectile breaks up, the center of mass will continue traveling as if nothing has happened. The center of mass of the pieces, no matter how many pieces, would travel along the blue line. Do you think you understand what I just said? On a scale of 0 to 10, please. So, I mean, it's easy, right? If you have a ball falling, it will fall like this, right? Well, obviously not like this, but a ball will fall just down like this. But let's say if the ball breaks into two pieces, and one piece travels like this, and the other piece travels like this, the center of mass would be here. Piece one, piece two, center of mass. So basically, if you drop a ball and it explodes halfway, if you can find the first piece, you will immediately know where the second piece is. All you need to do is just weigh it, and you will find exactly where the second piece is. All right? Does that? And it works for even if you don't throw it vertically. If you throw it at if it's a projectile, if you throw it like this is what happens normally. But if it breaks down into two pieces, one piece will land somewhere here. The second piece will land somewhere here. But the center of mass will land where it would have landed if they didn't break up. Okay, and that makes the problem incredibly easy. Well, I mean, if you know how to calculate the range of a projectile. I'm going to be lazy here, and I'm just going to use my system. I'm just going to change the angle to 30, and I'm just going to shoot, and I'm just going to measure the distance where it lands. So we know that the one piece lands 30 meters from the launch point. You know what? I'm not going to do that. Okay, so we know that one piece lands 30 meters from the launch point. And we know that the range, well, let's round it up, 80 meters. We know that this is 50 meters. So the other piece, so if this piece goes this way, the second piece must land symmetrically. So another 50 meters away, 50 meters. So overall, answer, it will land 130 meters. You see how incredibly easy this question becomes. I mean, assuming you know how to calculate, but you know how to calculate the range. There's a formula for the range. I'll try to remember it. The range is 2 v squared multiplied by sine 2 alpha and half gt. No, 2g. Does that sound right? So time is 2v sine alpha over g, and v cos alpha 2v sine alpha over g multiplied by v squared. Okay, there's no 2. All right, so there's a formula. So that's 30 squared multiplied by sine 2 times 30, so sine 60 divided by g, well, divided by 10. So that's 3900 times sine 60. Sine 60 is square root of 3 over 2. So 900 times sine 60 divided by 10, 78 meters. Okay, slightly off, but you got the point. You know, and once you've calculated this, if you know the mass of the first piece and you know the mass of the second piece, and in this case they are the same, but if you didn't, if you find one piece, you know exactly where to look for the other. I think that's quite fascinating. Okay, so finally we get to the tough questions. A particle of mass m traveling at speed v hits a stationary particle of mass m over 2 and deflects by 30 degrees. The collision is absolutely elastic. That means kinetic energy is conserved. Find the velocity of the second particle. So we need the velocity and we need the direction. Let's call it beta. Okay. So momentum is conserved in 2 directions. The momentum is conserved horizontally. Where momentum is mv before is equal to, now we break this down into, let's call it v1 and let's call it v2. So this is v1 cos alpha, this is v1 sine alpha, this is v2 cos alpha, and this is v2 sine alpha. Oh, sine beta, sorry, cos beta. So mv, that's the momentum before. Now momentum after is m, right? M v1 cos alpha plus m over 2, that's the mass, multiplied by v2 cos beta. That's the first equation. Vertically, Vertically, momentum is also conserved. So initially, there's no vertical momentum. Now we have V1 sine alpha, Vm V1 sine alpha minus m over 2 V2 sine beta equals to 0. So that means that this momentum is effectively equal to this momentum. Not, yes. All right. And that's the second equation. Now, the third equation is conservation of energy, kinetic energy conservation. We have conservation of kinetic energy. That means 1/2 mv squared is equal to the kinetic energy of this particle. So 1/2 mv1 squared plus 1/2 m over 2 v2 squared. I may have rushed this, but how well do you understand these three equations? How well do you understand these three equations? On a scale of 0 to 10, please. So momentum is conserved horizontally. I've written out momentum mv is equal to this momentum plus this. That's what I did. Vertically, this momentum plus this momentum has to equal to 0 because there's no horizontal momentum initially. And then the kinetic energy, just kinetic energy of the first particle, kinetic energy after the collision, plus kinetic energy after the collision. Now, the physicist in me says that I have solved the problem. I have, because that's where physics ends. This is the end of physics. Physics. All you need to do now is solve the three equations. And that's a mathematician. You need a mathematician to do that. You have three equations. You have three unknowns, V1, V2, and beta. Right? Three equations, three unknowns. That's it. Unknowns. V1, V2, and beta. Everything else is known. Okay. Well, that's what we're going to do. It will take us some time. So first of all, I can see that m cancels. In every equation, m cancels. That's nice. So let's write them out. I'll need some space, so I'll just write them as V equals V1 cos alpha plus 1/2 V2 cos beta. So just copied this equation. So V1 sine alpha equals 1/2 V2 sine beta. And finally, 1/2 V squared equals 1/2 V1 squared plus 1/4 V2 squared. So all we need to do now is just find a reasonable approach to solve these three equations. Any suggestions? Well, I would suggest substituting alpha. Alpha is known, so that would probably be useful. Well, I'll express. Yeah, I'll substitute alpha. So V equals V1 cos 30 degrees is square root of 3 over 2 plus 1/2 V2 cos beta. V1 times a half. Well, okay, times a half equals 1/2 v2 sine beta. And I won't do anything with that one yet. Okay. All right, so let's express v1 from here. So v1 is v2 sine beta. And we can substitute that into 1. So v is equal to v2 sine beta. So I've substituted here, multiplied by square root of 3 over 2, plus 1/2 v2 cos beta. All right. And now I'm going to multiply this by 4. It's going to be 2v2 v squared equals 2v1 squared equals v plus v2 squared. And now I'm going to substitute this into this third equation. So it's going to be 2, open bracket, v2 sine beta square root of 3 over 2 plus 1/2 v2 cos beta squared equals 2v1. I'm going to substitute that. It's going to be 2v2 squared sine squared beta plus v2 squared. I won't touch the first two equations. I'm going to work with this one. So I'm going to expand. It's going to be 2 v2 squared sine squared beta 3 over 4 plus 2 v2 sine beta square root of 3 over 2 multiplied by 1/2 v2 cos beta. So I'm just using square of sum formula plus 1/4 v2 squared cos beta cos squared beta equals 2v2 squared sine squared beta plus v2 squared. Now we can see that v2 squared cancels, and we're left with 2 times that, so it's 3 over 2 sine squared beta plus 2 cancels, it cancels again, square root of 3 sine beta cos beta plus 1/2 cos squared beta equals 2 sine squared beta plus 1. And here I'm going to do a trick. I'm going to replace 1 with sine squared beta plus cos squared beta. There's going to be 2 sine squared beta plus sine squared beta plus cos squared beta. Okay, looks scary, but bear with me. All right, so this is 3. So 3 over 2 minus 3, so it's minus 3 over 2 sine squared beta plus square root of 3 sine beta cos beta plus cos beta, so it's minus 1/2 cos squared beta equals 0. And now I divide by cos squared beta, and I have minus 3 over 2 tan squared beta plus square root of 3 tan beta minus 1/2 equals 0. What does that look like? What does that look like to you? Assignment 1, quadratic, of course. Now it's a quadratic equation. If you make a substitution, you can do minus 3 over 2. I'm not going to bore you with solving the quadratic. So tan beta is equal to minus b, so minus square root of 3, plus minus square root of b squared, so 3, minus 4 multiplied by minus 3 over 2 multiplied by minus 1/2 divided by 2 multiplied by minus 3 over 2. Turns out that this is going to be square root of 3 over 3. Actually, yes, because this is 4 cancels, and this is 3 minus 3. This is 0. So this is going to be minus square root of 3 plus minus 0, and divided by minus 3, which is square root of 3 over 3. Right, so it does work. That means beta is 30 degrees. We found beta. And now we just need to find V1. Do we? Okay, beta. All right, so no, yes, now we can substitute that into here. So from here, V is equal to V2 multiplied by sine 30 multiplied by square root of 3 over 2 plus 1/2 V2 multiplied by cos 30. And from here, V equals V2 multiplied by, so that's 1/2. So square root of 3 over 4 plus, oh, what do we know? Square root of 3 over 4, which is, so V equals V2 multiplied by square root of 3 over 2. So V2 is 2 divided by square root of 3 of V, which is approximately 2 divided by square root 3. It's approximately 1.15 of V. So we find the direction and we found the speed. That's it. That's all we need. That's all we needed. V is equal to 2 divided by square root of 3. V2 is square root of 2 divided by square root of 3. I mean, if we knew V, we could substitute that. I would really want you to appreciate how this problem only becomes difficult once you try to solve the equations. But until then, the physics is quite straightforward. Would you agree with that? Because you've written out the physics, you double check. Okay, I've got 3 equations, I've got 3 unknowns. Is it solvable? Probably yes. And the rest is just your ability to manipulate equations. Of course, it's a really important skill, but physics is not that hard, honestly, until, yeah. I have to say that one of the subjects I really didn't enjoy at university was mathematical physics. It was just like, you do the physics in 2 minutes, and then it's a painstaking differential equations, which make you want to climb up the wall. Some of them, partial differential equations, like, yeah. Anyways, problem 6. Calculation-wise, it's simpler. So you have an object which is trying to go over a hill. So the question is, will the mass go over the wedge? what do you need to look at? What things do you need to consider when answering the question, will the mass go over the wedge? Can the mass go over the wedge? It is frictionless, yes. Oh, the wedge is stationary. With enough momentum. Well, yes, well, but how do you judge whether it has enough momentum to go over? What do you need to look at? What simple calculation do you have to make in order to tell? Yes, kinetic energy. You have a conversion of kinetic energy to gravitational. So you have kinetic energy converting to gravitational potential energy. So you have 1/2 mv squared equals mgh, right? As the puck goes on top, you have a conversion of energy. All right, so m cancels. V squared is equal to 2gh, and V is equal to square root of 2gh, and that is square root of 2 times 10 times 1.2, square root of 2.4, square root of 24, which is approximately 4.9, square root of 24, 4.9, yeah, meters per second. In order to go, you need 4.9 to go over, and your speed is 5. So do you think it will? Looks that way, yeah. Speed. Speed. This is 5 meters a second. Well, there's a catch. Does anyone see the catch? What is that? Is the I might not have made it obvious, but the wedge can move. The wedge can move. The wedge is not fixed to the ground. So that would happen if the wedge were fixed. But because the wedge can move, while the mass is climbing the wedge, it will transfer some of the momentum to the wedge. If the wedge can move, some of the momentum, some of kinetic energy will be transferred to the wedge. Yeah. Okay. So you need to consider in order to find the minimum speed to go over the wedge, you need to consider the case where the before is you have the wedge like this. This is the before, and then the after. And then the after is when the mass is on top of the wedge and they're both moving at the same speed of u, for example. In the borderline case, mass stops on top of wedge and they both move together. All right, so we have conservation of momentum. Momentum together. Momentum. So we have mv equals m plus m multiplied by u, because that's the mass of the hill. That's the mass of the object. And they're both moving. So before it was just the puck moving, and after it's the puck and this. So this is m. We know that m is 1 kilogram and this is 5, so it's 6. No, it's fine. We can keep it that way. Energy. So we have 1/2 mv squared equals gravitational energy, mgh, plus the kinetic energy. So it's 1/2 m plus m multiplied by u squared. All right. Okay, and then we solve these. We substitute m is 1, so that's equal to. So v is the minimum speed. So we're not substituting v. Yeah, we're not substituting v at the moment. We're looking for v. And so now from here, I have 1. So 1v is equal to 6u. So u is, oh, that's fine. We can find u. So 1/2 m. I won't have multiplied by 1 multiplied by 36u squared equals 10 times 1.2 plus 1/2 multiplied by 6 multiplied by u squared. And from here, it's 18 u squared equals 12 plus 3u squared. 15 u squared equals 12. U squared equals 12 over 15. U is square root, so 12 over 15. That's 4/5, 0.8. Square root of 0.8. Root of 0.8, which is approximately 0.89 meters per second. That's the speed of them together. So v is 6u. That's equal to 6 multiplied by square root of 0.8. 6. And that is 5.37 meters per second. So that's not enough. So that's not enough to go over. Okay. That's it. Yeah, so it will go on top and then slide back. The wedge will carry on moving. That's the minimum speed to go over. Minimum speed to go over. And since we have the minimum speed is, our speed is less than the minimum, then we can solve it just like a normal collision. All right. And if it did go over, If it did go over, then the wedge would stop. The wedge would stop, and then the puck would carry on moving. It would go over, so it would start moving a little bit, and then it would actually move. Would it move back? Yeah, it would move back to the original position. And yeah. No. Can't move back to the original position. Oh, anyways, the wedge would stop. That's the important part. The wedge would stop. Okay, so I hope that was useful. Hope some of it was insightful, and yeah, hopefully it was enjoyable. So see you all in a week. Bye. See you. Welcome.